Hi everyone, so I'm going to be talking about digital to analog, and there's three different things that we have to remember in digital to analog. There is amplitude shift keying, frequency shift keying, and phase shift keying. And then the phase shift keying and amplitude shift keying is what can make up that quadrature amplitude modulation. So we'll look into what all of this means here. So here we got the amplitude shift keying. So for the amplitude, we can see here on the graph, the amplitude represents the y-axis, and then there's a time on the x-axis. So amplitude here, you can see we got these bits which are being translated over a transition medium, which is 10110, and we want to know how fast it's going in order to translate certain signals. So here we got 10110. So we want to be able to look at these, the amplitude shift keying. So we look at the amplitude. Amplitude is how high it is, or how many cycles essentially is within one bit of this amplitude. So here in an amplitude, you can see here we have a certain height of these different sine waves. And here for this first one, the first cycle right here, you can see if we look at the peaks here, we go one cycle for that. So one phase, you can see here as that amplitude goes up above the positive area of the graph and the negative area of the graph, that's 1. And then in order to count the next one, this is 2, and then 3. So we have 3 different peaks here within this one bit. So that means that we have 3. We write down the number 3, and how many of these ones do we have within this 1 second time frame, which is 5 baud for this example. So what we want to do is we want to multiply the number of ones, the number of different peaks here, by that number. So it's 3 because we have 3 ones. So it'll be 3 times 3, and then that'll equal to 9 hertz. And then we got the next one here, which is frequency shift keying. Frequency shift keying, it's FSK. So here we got the same thing, amplitude over time. So the time is the x-axis, amplitude is the y-axis. But here you can see there's a difference in the chart. So before, the zeros are flatlined, but the ones have certain peaks to it. And here in frequency shift keying, you can see here that the ones have 1, 2, 3. So within one bit, we have 3 peaks here, 3 cycles. And here in the 0, we have 1, 2. So 2 of these cycles within that 0 bit. So we need to, this means that since we have 2 different peaks within the different bits here, the 2 different bits, that means we're going to have 2 different values that are going to be translated over this transition medium. So we have a logical 1, which is the ones here, and we said that it has 3 cycles within 1 bit, so that's 3 divided by 0.2 is this baud, well, it's this 1 second. Within 1 second, we have 5 bits, so 1 divided by 5 is 0.2. So we're looking at 1 bit at a time. 1 bit, we take 3 divided by 0.2. That would give us 15 hertz. And then we're looking at the zeros now. So 1, 2, so that'll be 2 divided by 0.2. That'll give us 10 hertz. So that means we're going to be passing over both that 15 hertz and 10 hertz throughout this transition medium. And then there is the phase shift keying, so PSK. And we have the same thing, we have time and then amplitude. So what we have here is we have the ones and zeros again, the same pattern, but what's different here is we're taking the same cycle pattern, but we're just flipping it. So you can see here we have 1, 2, 3, but now instead of this where it starts here, it goes up and then down. If we look at 0, it starts from going here to all the way down and then up, but that's 1, then this is 2, and this is 3. So you can see here they both have 3 cycles. We're still going to be passing over 2 different values throughout this transition medium, but they will be the same because of this phase shift keying. It's just a shift in the phase. A phase shift just means it moves left or right along the x or y axes, so it's just another phase. If it was starting here like this, you can see it would have gone up and then down, but because we moved this graph over by phase shift, you can see here now it's starting to go down and then up. And what we have here for the logical 1, we have 3 divided by 0.2, 15 hertz. And then the 0 is same thing, 3 divided by 0.2, that's 15 hertz. So we're going to be passing over 2 values, which is 15 hertz and 15 hertz along this transition medium. So for this one, we want to look at the constellation diagrams. So here in the constellation diagrams, it means this bit amplitude shift keying. So BASK, so we're dealing with amplitude still, but we're dealing with bits. So bits, if we're dealing with amplitude, we can really just only have something that's high and then flatlined. So there's only 2 possible different values here for amplitude shift or bit amplitude shift keying. So what we do is the 0 is flatline, so we stick it at the 0, 0, 0 portion of the graph, and then the amplitude we can just put it here at the 1 or this 1 volt because we're going to be having some sort of amplitude to it, so it changes where this position is. And then we have the bit phase shift keying. Bit phase shift keying, because it shifts left or right along the x-axis, we're going to be having the 0 on the negative part of the x-axis, and then the 1 bit on the positive side of the y-axis. And here we represent it like this. And then we have the quadrature phase shift keying. Quadrature phase shift keying, quad means 4, so you can see it's in a circular shape within the graph, and we have 4 different quadratures, 4 different quadrants, so 1, 2, 3, and 4 quadrants, and we're dealing with the phase shift keying. We're still moving over the phase, so because the phase deals with left and right side, we're able to move this along based on the distance from the center of the 0, 0 portion of the graph. And you can see here we can represent this as 1, 1 on the right quadrant, top right quadrant, and then on the left side we have 0, 1 bit, and then the bottom left is 0, 0 bit, and then the bottom right is 1, 0 bit. And if you draw a circle, you can see that it'll go through that line. And really the amplitude is just this, it's like a invisible line from the center to that dot. And then we got different ways we can represent quadrature amplitude modulation. So here we got 4 quam, 4 dots. It could be represented like this along the x or y axes with 4 dots, or 4 quam just within one quadrature. Or here, for example, we have 16 quam. We can put it in different parts of the quadrants, and we have 4, 4, 4, 4. We have 16 dots, so 16 QAM. So hopefully that gives you a little bit of insight as to how we can use different waves in order to represent how sound can be transferred throughout a transition medium, and how we can represent ones and zeros as it's passing through that transition medium, whether there's zero amplitude or there is a peak to it, and how we can modify those peaks in different transitions of amplitude, phase, or frequency, and dealing with how we can look at different quadrants and representing it in terms of 0 volts and 1 volts, and how it can be represented in different quadrants. And don't forget to like, share, and subscribe to this video if you enjoyed it. And let me know down in the comments below if you have any questions about any of these diagrams or these different ways that I've explained the concept.